Hello everybody, I'm Cristiano Longarini and I'm a postdoc at the Institute of Astronomy at the University of Cambridge. I'm currently working with Kathy Clark, and thank you very much for inviting me to give this seminar. And what I will be talking about today is the process of gravitational instability and how this can help to understand the process of planet formation in young protostellar disks. So thanks to ALMA, we are now able to look into planet formation in real time. I think all of you know this very famous image. So these are images of dust continuum emission from protoplanetary disks. These are taken from the D-Sharp large program. And as you can see in these beautiful images, these disks are not smooth at all. So they show a lot of substructures such as gaps, rings, spiral, non-axisymmetric features. And of course, understanding the origin of this substructure is of primary importance. There are different physical mechanisms that can explain such substructures, but one phenomenon that is able to explain all of this substructure is planet-disk interaction. So it is possible that in some of these disks, planet-disk interaction is going on, so there is an embedded protoplanet. And nowadays it's possible to infer the presence of protoplanets with indirect or direct methods. For example, it is possible to hydrodynamically modeling the emission from these systems. So we model, for example, the planet-disk interaction, we post-process these simulations, and we compare with actual data, as in the case of the H-tau here shown in this slide. And it is also possible now to infer the presence of protoplanets, of embedded protoplanets through kinematic signatures, in particular by detecting the gravitational perturbation of an embedded protoplanet inside a protoplanetary disk. And finally, for some disks, it is also possible to directly image the protoplanet or the circumplanetary material, as in the very famous case of PDS-70. And so under the interpretation that let's say, most of the substructures we observe with ALMA are generated by planet, a consequence is that the process of planet formation must happen very early in protoplanetary disk lifetime. And when protoplanetary disks are young, they are more massive. This makes sense under a theoretical perspective, since they are accretion disks, but also under an observational perspective. Indeed, if you look, for example, this plot that shows the cumulative mass function of protoplanetary disk in different star-forming regions, it is clear that there is a trend of this quantity with the age of the system, of the star-forming region, sorry, showing that older protoplanetary disks are likely to be less massive. So young protoplanetary disks are massive. And when a protoplanetary disk is massive, the role of its self-gravity and possibly the role of gravitational instability may be important in their evolution and possibly in the process of planet formation. Since I want to talk a bit about planet formation, so one of the most famous theory for planet formation is the core accretion theory. This is a dust-based theory, so the idea is that dust is growing from micrometer size, eventually forming planets. And while the first and the last stages of this scenario, so like growing from micrometer to millimeter, centimeter, and then evolving planetary cores and eventually forming giant planets, giant gaseous planets is pretty well understood, there is a problem in this theory that is the step of planetesimal formation. So how can we go from millimeter size to meter, kilometer sizes? And the main problem here is the radial drift. So an alternative theory is the gravitational instability, and I call here gravitational instability the classic scenario. So historically, gravitational instability is thought as a planet formation scenario, since, as you can see from this hydrodynamical simulation, under given condition, a self-gravitating spiral of a protoplanetary disk can fragment, forming a gravitationally bound object that has an initial mass of the order of 1 to 10 Jupiter masses. But soon we realize that this initial mass is too high to form a planet, because then this object will start accreting material, eventually forming a low mass stellar companion. So also gravitational instability in this classic scenario has problems in explaining the formation of planets. And so what I want to talk about today is a different perspective on gravitational instability, and in particular, understanding the interplay between dust and the gravitational instability. And this is like a mix between the core accretion that is based on dust and the gravitational instability theory for planet formation. And so the idea is that what happens to dust grains in GI spirals. So just a brief slide to summarize what I mean with the gravitational instability. So gravitational instability is simply a linear hydrodynamical instability that takes place in a self-gravitating system. And this is the dispersion relation for such self-gravitating disk. I mean, I don't want to go into the detail of this, but what's important is this parameter that I wrote in the bottom of this slide, Tumri Q parameter, that is basically measuring the likelihood of a disk to be gravitationally unstable. This parameter is proportional to the disk temperature and inversely proportional to the surface density of the disk, meaning that cold and massive disks are likely to be gravitationally unstable. And the threshold for instability is Q equal 1. And so this is for the linear theory. Then what we can do is to run hydrodynamical simulations by varying parameters of the disk, such as the disk to star mass ratio, or what I call here beta. Beta is the cooling factor, so it's just determining how strong the gravitational instability is. And you can see that the morphology of the spirals can really can vary a lot by varying these two parameters. And in particular, you can see, for example, a scaling with the disk to star mass ratio of the number of spiral arms of this disk. And so, as I told you, I'm interested in understanding the interplay between dust dynamics and gravitational instability. And when we studied these, there are two main phenomena that we need to take into account. The first one is dust trapping. Indeed, dust particles tends to accumulate inside gas spiral arms, since the gas spiral arms are pressure maximum. And so it is possible to significantly increase the gas to dust ratio inside these structures. But at the same time, dust particles can be excited when they interact with the spiral arms. And in particular, we can imagine like a spiral arm that is kicking, this is giving a kick to these dust particles, and so they can be excited. So there are relative motions between dust grains, and this is stabilizing the dust. So, I mean, it's going against, let's say, the increase of the dust to gas ratio. And so what we want to understand is the interplay between these two effects, and we want to understand what are the best conditions for dust to directly collapse inside gas spiral arms because they are because the high concentration. And so what I'm doing now is to use 3D hydrodynamical simulations to study this problem. And in particular, what I'm doing now is just a numerical experiment. I don't really want to reproduce an actual system. So what I'm doing is to take a simulation, and I'm imposing that all dust grains in the simulation have the same Stokes number, so that I can really study what is how the concentration of dust grains in spiral arms and how the relative motions between dust grains depends on the Stokes number. And in particular, I'm running simulation with Stokes number from 10 to the minus 3 to 100. And here in this slide, you can see the morphology of the dust density for these different Stokes number. And in particular, you can see that for very low Stokes numbers, so Stokes to 10 to the minus 3, dust density is basically tracing the gas density. So dust and gas are behaving in the same way, and there are no particularly interesting phenomena happening there. But then when the Stokes number is of the order of unity between 0.1 and 1, you can really see that the dust spirals are really thin because dust is concentrating inside these structures. And then when we increase the Stokes number, you see that the spiral structure becomes weaker and weaker because the aerodynamical coupling is less strong. And so now I would like to show you precisely what happens for different Stokes number. So for Stokes number lower than 10 to the minus 1, the idea is that the velocity dispersion of dust grains is low because the drag force is damping the kick from the spiral arm. But however, for such small Stokes number, dust trapping is not really efficient. And so the idea is that here the dust is not really concentrated inside spiral arm because it's just tracing the behavior of the gas. Then we have the most interesting regime that is between Stokes 0.1 to Stokes 1. Here, the velocity dispersion is at its minimum because the aerodynamical coupling with the gas is strong enough to create correlation in the motion of dust particles inside spiral arms. And that's why the velocity dispersion is really low here. And as for the dust trapping, this is the Stokes number regime in which the dust trapping is most efficient, and we collect very efficiently dust grains inside spiral arms. And so these are the best conditions, I mean, at least in theory, for dust to directly collapse inside these structures. Then we have the regime of Stokes number between 1 and 10, where dust particles becomes more and more excited because the aerodynamical coupling is weak enough that the kick of the spiral is exciting relative motions. And in particular, here there is a scaling of the dispersion velocity as the square root of Stokes number. And as for the dust trapping, here it becomes less and less efficient because the drag force is weaker. And finally, for high Stokes number, so for Stokes number higher than 10, we basically have a stable dusty layer that is not even tracing the spirals in the gas. And so if we want to understand whether dust collapse happens or not, we can use this, we can use a proxy that has been discussed in several papers in the past. So we can try to relate the local dust to gas ratio, so the concentration of dust particles, with the ratio between the dust velocity dispersion, the one I call CD, and the sound speed of the gas. And in particular, when the dust to gas ratio is higher than the ratio between the dust and gas velocity dispersion, what happens is that the dust is gravitationally unstable itself. This is not, it is not given for granted that the dust would collapse, but this is a strong indication that dust is unstable. And so we can look this relationship in this plot where I show you the dust to gas ratio against the ratio between the dispersion velocity dispersion, and each point is a particle in my simulation. And this is for Stokes 0.01. So the black line shows this the threshold I discussed before. So all the points that are above the line are unstable. And in here you can see that really a small amount of dust particles are respecting this condition. But if we increase the Stokes number, like 0.1 or even 1, we see that there is a significant fraction of particles that are in this unstable regime. And if we want to map their position, you can see here the yellow points. So these particles are likely to be inside the spiral arms, where the dust concentration is higher and the velocity dispersion is lower. And then if we, for example, study for higher Stokes number, 10 or 100, you see that here, basically no particles are in this region of the parameter space. So what we did also back in 2023 was to run a simulation with a fixed grain size rather than a fixed Stokes number to see whether this we could observe directly in the simulation the collapse. And we did for a couple of cases. And here you can see that we can create this clump of dust particles with a mass of the order of 1 Earth masses. And as you can see from the right panel of this slide, the collapse is actually happening just in the dust component. So the gas average density is constant, while for the dust particles, you see that there is like a huge increase of the quantity. And so the idea is that with this mechanism, we are in principle able to form planetary cores directly through dust collapse. And so a question we also have is to understand what happens afterwards. So this is possibly a way to form a planetary cores in young systems, but these cores can then migrate, and in particular, since they are their mass is small compared to the thermal mass, they will undergo type 1 migration. And we know that the time scale for type 1 migration is really fast, but at the same time, these planetary cores are in a very dense environment because, as I told you before, these disks are very massive since they are likely to be self-gravitating and gravitationally unstable. And so also the time for the planetary core to reach the thermal mass through accretion of gas and then open a gap and stop migration is also pretty fast. So the idea we had with the master student in Cambridge was to perform very simple hydrodynamical simulations where we wanted to compare these two time scale and to understand whether it's possible for a planetary core to reach the thermal mass and stop type 1 migration. So this is a simulation we run. So in the white dot is the planetary core. So you can see that in this first stage, the planetary core is migrating inwards, but at the same time is increasing its mass because it's accreting material. And you can see here that it reaches the thermal mass and is able to finally open a gap. And this is, for example, these are two plots where we show the evolution of the radius of the planet. So the radius here, I mean the semi-major axis of the planet as a function of time, and the mass of the planet compared to the thermal mass as a function of time. And for this specific simulation, we see that planet migration is stopped because the planetary core is able to accrete a lot of material thanks to is able to accrete enough material, to reach the thermal mass. Of course, we have also other simulations where we see the opposite behavior. So where the type 1 migration time scale is too fast, and this planetary core is accreted by the central object. And here I'd like to leave you with my conclusions. So in this talk, I showed you a possible way to form planetary cores in young photostellar disks when we consider the interplay between dust dynamics and gravitational instability. And we show that the favorable Stokes number for this mechanism to act is between 0.1 and 1. We are now working also in determining what is the collisional velocity between different particles that is a very important quantity in terms of dust growth. And we also show that in a region of our parameter space, for these planetary courses, they are able to survive against migration. And yeah, thank you very much for your attention. I'm really happy to take questions. Thank you.
That's great. Thank you very much. That was an excellent talk. Does anyone have any questions that they'd like to ask? I'll ask one that I was thinking about. So you can form these like planetary cores from this dust sticking together sort of locally, or well, collapsing locally, I should say, really. What kind of timescale does this happen over? When you go from like micron to the size of this Earth-sized core, how long does that take?
Okay, so here I must say that in this simulation, we already started with grain size of the order of centimeters. So, I mean, grain size for which the Stokes number is of the order of unity. So we didn't simulate the previous part. We just start from, let's say, the most favorable condition. But as you can see here in the plot on the right, we can have an idea of the time scale for this dust clump to form and eventually collapse that is of the order of the orbital time scale, of the dynamical time scale. So the collapse itself is a really fast process. How to arrive at that point? So how to arrive at the point that we have Stokes 0.11 particles? This is another question, and I mean, I haven't studied this in my work so far, but yeah, this is a good point actually.
Okay, great, thank you. Does anyone else have anything else they'd like to ask? I've got one more follow-up. Oh, no, go on, yeah, Richard?
Hi, Cristiano. Thanks for describing what's a really nice work. I think I'd like to talk with you about this at length at some point in time.
Yes.
But this is obviously not the right forum. I think at the moment there's I guess a couple of things. One thing about the long-term evolution of these planets. Did you check whether the accretion luminosity of the cores as they're growing is enough to prevent them from undergoing runaway gas accretion, right? Because ultimately to accrete gas, they have to be able to cool. And in these outer parts of the disk, you don't actually need that much accretion to overcome this.
Yeah, that's a very, very great point. We haven't checked that at the moment. I think we have everything we need to check from the simulations, but we haven't done it so far. And this is a very good suggestion. So it's something to be controlled. Thank you very much, Richard, for this suggestion.
Anyway, let's chat about this more another time.
Yes.
Thanks for nice talk.
Yeah, definitely. Thank you.
Anybody else? I've got one other one I wanted to ask as well. Can you, in a single simulation, can you form multiple of these cores? And is it possible for then these cores to collide later and form a larger planet or something later?
Yes, so in my simulations, so what happens is that the simulation stops at the formation of the first core because of my stopping time calculation. So the idea is that the stopping time is inversely proportional to the total density. And so this means that if we collapse in dust, the stopping time goes to zero. And so the simulation is not able to deal with this. But in other simulations, for example, from Sal Rother of last year, where he used a slightly different drag force implementation, he could evolve afterwards, so after the first collapse. And what he sees is that the collapse happens in different parts of this. So there is a formation of different dust clumps, and I'm not sure about the interaction between them. So this is something I would need to check, but definitely, I mean, from his simulation, what I remember is that you can form really a lot of clumps, so they are probably likely to interact one with each other.
Yeah, that makes sense. Cool. Thanks very much.
Thank you.
Okay, then I think then with that,